Lab 3 Circuits by Caitlin Schmidt. For the introduction, the purpose of this lab is to predict how circuits with series and parallel resistors react, and to apply the principles of energy conservation and current/charge conservation, and measure the conventional current and potential differences within these circuits using multimeters, investigate characteristics of resistors and capacitors, and the assumptions are to neglect external forces and electric field in the connecting wires. So this is the introduction part, and it includes the key findings. So it has the potential difference for all the resistors and the change. And then it has the charge and discharge time for both the 10 ohm light bulb and the 20 ohm light bulb. Here are the key principles, which include the node rule, and it's the total electric current flowing into any node in a circuit must equal the total current flowing out of that junction. And then there's the equation. The loop rule, which is the conservation of energy. It's the sum of all changes in positive in electric potential in a closed circuit must equal 0. Ohm's law, which is the voltage across a resistor, and capacitance, which is the amount of electric charge a capacitor can store. So the experiment overview for the series circuit, and we have the initial conditions listed. The system is the circuit and the surroundings is everything else, and there's just a diagram of what it would look like and a picture of what it actually looks like. So here are the calculations for that part. Calculated the current and also use Ohm's law to get that part. And we also did the loop potential difference. And the measured/calculated values turned out to be close to 0, but not actually 0, and the expected should be 0. So here is the potential versus position on a circuit chart, and this basically just shows that the potential of energy goes down when more ohms are added to the bulb closer to the emitter. So when you put emitters in parallel, the results are that there's a huge current spike and there's like a 3 times increase, and the current bypasses the resistor and goes on a new path. So the problem is that ideal emitters have resistance in parallel, a short circuit path forms, and this drastically reduces overall resistance, so the total current spikes. And basically, emitters need to be in series to accurately measure the current. Now for the experiment overview part of the RC circuit. So I have the initial conditions listed, the system, the surroundings, and the results. Also a picture of the RC current and a diagram of what that should look like. So this is the round trip potential plot. The above equation is what it's should be, and the below is what it is actually based on. And I included the parameters, which is the initial voltage, resistance, and the capacitance. And overall, the plot analysis. So the observation is that there's a shallow negative slope, and the comparison is that the expected decay, which is the top equation, should have occurred much faster than the actual result, which is the bottom equations. Okay, now for comparison and errors. So the model discrepancies are the observed discharge time and the round trip potential plot, and potential errors are that ammeter was not precise or calibrated correctly. The experiment also did not account for external factors, and those could have influenced results. And there's also maybe unreliable data due to human error. So this is the discussion for what if, and it's asking what if you charge a capacitor with no resistor in the circuit, how quickly would our ideal model predict the capacitor to reach full charge? Would this prediction happen in real life? Explain. Use an ammeter to measure how long it takes to charge a capacitor when connected directly to the battery, and then discuss. So when charging a capacitor, the ideal circuit model would predict that the capacitor reaches full charge instantaneously. However, that is not possible in the real world because every component has a small non-zero resistance. This resistance creates an effective RC circuit because it requires a finite amount of time to charge the capacitor. The measured change in time was 6 minutes. This shows that the resistance in the actual circuit slows the current flow and prevents that instantaneous change from happening. Thank you for your time.